Now that we have related pressure, volume, and temperature of an ideal gas, we're going to move in and talk about how energy and enthalpy of an ideal gas is related. And really, it only depends on temperature for an ideal gas. Okay, so for that reason, once I know temperature, I should be able to find the energy or enthalpy of an ideal gas. Okay, now ideally, we use a table, right? Whenever I have a table, I should use a table. We have table A22, which it tabulates air. And again, A22 is only dependent on the temperature. So if I know the temperature, I can directly look up either U or H in the table. Okay. Table A23 has gases like oxygen, carbon dioxide, nitrogen. Okay. And it also lists, again, directly from temperature, the enthalpy or the energy. Difference is it's giving me U bar and H bar. So to get it into the terms that we like, the specific internal energy, we need to take the value we get and divide it by, again, the molecular weight of whatever gas it is that I'm looking at. Okay, because in our terms, we're always going to be dealing with things in mass terms. So when you see U bar, just divide that by the molecular weight to get to U, which is in terms of mass, like we like it to be. Again, if you have a table, use it. If you don't have a table, the approach we need to take is using a specific heat, which is not ideal. Okay. Again, the table values come from experimental data, whereas the specific heat idea starts getting a little fuzzy, and we'll talk about that as we go on. We talked a little bit about specific heat for solids and liquids. Now, with gases, we have two different kinds of specific heat. I'll let you look in the book for a definition. It kind of clouds what I want to say about it. So I'll let you look at that if you're interested, exactly what CV and CP mean. But what I need you to remember is that CV is related to energy, whereas CP is related to enthalpy. So CV equals du dt, CP equals dH dt. And again, this is basically the definition of these specific heats. Okay, just remember CV is related to U, CP is related to H. Now, again, what we're most interested in is finding the change in energy, the change in enthalpy. So just rearranging this equation and taking an integral, I can find that the change in internal energy is the integral of CV times dt. And the change in enthalpy is CP times dt. Okay, now, the thing is these specific heats are dependent on temperature. Okay, so we really need an equation of this in order to get it, and we don't really have that. However, we do have a table that puts in what we call a specific heat function. Okay, and again, you would only want to use this for gases that are not in table A22 or A23 as above. Okay, which is very rarely in this course. Okay, but I can find CP as a function of temperature through this, and the table actually tabulates alpha, beta, gamma, delta, and epsilon. Then I could take that and take an integral of it to find things. Now, we don't use this very often, okay, with one exception, when I have a monatomic gas. Now, these are the noble gases. Monatomic means they exist as just one molecule. We're talking about helium, we're talking about neon, we're talking about argon. Okay, and if you have one of these gases, then in fact the specific heat is constant. Okay, and the CP is approximately equal to 2.5 times R, which is the universal gas constant, again, for each thing. Again, you look up R bar divided by the molecular weight. And then that makes our equation pretty easy, which is the change in U is CV delta T. The change in H is CP delta T. So again, just what I mainly want you to remember is the relationship between CV and U and CP and H. Okay, and again, this equation only holds true for monatomic gases, or if the problem explicitly tells you that the specific heat is constant. Please remember that the specific heat in general is not constant. You only want to use this equation if you cannot find it any other way, or it explicitly tells you to use specific heat, or it's a monatomic gas where the specific heat actually is constant. So if this substance is helium, neon, or argon, then you absolutely can use this because specific heat is constant. If it's any other substance, I would prefer you use a different approach than constant specific heat. If there's a table, use it. If not, then we have to start approximating using these specific heats. Okay. If it's argon, neon, helium, then specific heat actually is constant, and you can use the Boxen equation at the bottom here. Now, one more thing about these specific heats. I want to talk a little bit about the relationship between CV and CP. Okay, you'll remember H is U plus PV. For an ideal gas, right, PV equals RT, so H is U plus RT. Okay, now using our definition of CV and CP, again, I replace H with CP dt, U with CV dt, and then I have R times dt. I can get rid of all the temperatures, and I can relate CP to CV just by adding R to CV. Okay? So that's how I can, if I know CP, I can find CV, or vice versa, is using that equation. This one we use a little bit, is the specific heat ratio, which is, we call K, which is essentially CP divided by CV. Okay? And you could plug this into the above equation, and if you have K, you can find CP or CV using this equation here. Again, specific heats are only to be used when it explicitly says in the problem to use it, or it's helium, neon, or argon. Okay? Or it's some gas that I don't have a table for, either air or any of the ones in A23. Again, if you have a table, you should be using that to find your energy values.